Yeah, you're welcome, Randy. So first off, I guess I'll be covering the first 14 slides, and then Keith will take over after that. We will have a few poll everywhere questions. That information is in the chat box, but I also will have that on the slide for you to reference. And then feel free to ask questions as we go along. Specifically, if something is unclear, if you're like, hey, Matt, what did you really mean by that? Just pop it in the chat and Randy will interrupt me and we'll make it clear, because there's nothing worse than going on and being confused. So as you know, with some research, when you work on it a long time, you kind of gloss over it and you think, well, everybody understands it as well as we do. So sometimes we look through things through that lens. Anyway, I want to start by thanking Jim Sieveking for suggesting we postpone this. We were going to give this presentation in January, then changed our mind at the last moment based on his suggestion, which is good because I think there was a blizzard going on around that time. Now we have a potential squall line that will be moving across the eastern part of Central Region, so it's much more timely. And then finally, Keith and I want to thank Angela Mose, who was our Hauling Scholar in 2019, and without her, I don't think this work would have come to completion, especially at this time. And she was at Pathways also last year. She's at Norman now, finishing up her degree, and she'll be joining Central Region, the Cheyenne office, here in this spring. So to use the words of Simon Sinek, we're starting with the why. You know, why are you here? Why should you care about this? How will this be useful for you? And we think the main thing that you can take away from this is that we're going to provide a tool that you can use to produce better wind gust estimates in our severe thunderstorm warnings. If you look at this chart that Daryl Hertzman from Iowa State gave to me, you can see that nearly 80% of all of our severe thunderstorm warnings have a default or an initial wind gust of 60 miles an hour. So 4/5 of them, we're starting out with 60 miles an hour. If you compare that to hail, just under 50% of those start with the default of 1 inch. So we certainly think we can do better there. And that's going to be based on primarily information on the outflow boundary motion, or if you can't measure that, the speed of the thunderstorm, leading edge of the thunderstorm. But other things are important as well, such as the convective mode, the environment, and the time of day and time of year. So that will lead us to our first poll question here. So again, if you just text the phrase DHINTS 906, upper or lowercase, doesn't matter, to the number 22333, and then you can answer this poll question. So the question is, do you think it's harder to predict the maximum hail size or the maximum wind gust for our IBW tags in our severe thunderstorm warnings? Keith and I have our own preconceived notions about this. We wanted to get a feel for what the rest of the region was thinking about this and see if we are on track or not. And I'll show the responses here. People are probably still getting logged in. Okay. Okay, I was wondering if this is working, but we are starting to see some responses come in. And at least up to this point, we're seeing 100% for wind. And Keith and I argued that wind is harder to predict than hail. One of the reasons I asked this question was because when we submitted this paper for review, one of the reviewers actually argued against us, that hail was harder to predict and that there are a lot more tools for maybe wind than hail, which we disagreed with. And of course, this supports what we were talking about. So thanks for that. So before we get into the methods and the data, I just want to talk about, well, how would you use this tool that we're going to talk about? So it's really simple, really straightforward. You simply track the outflow boundary of the system, and here we have the reflectivity on the left and the spectrum width on the right. So if you can identify the outflow boundary, you track that, you get a speed. If not, you track the leading edge of the thunderstorm system. Note that we're not looking at the base velocity here and using the measured velocity from the Doppler. We're simply tracking the speed of the outflow or the speed of the system. And then you take that speed, let's say it's 30 miles an hour, and you multiply it by a factor, which we will refer to later as the wind gust ratio. So let's say that factor is 1.5. 1.5 times 30 would give you an estimated maximum wind gust of 45 miles an hour in this particular case that we have contrived here. So it's just that simple. You can calculate it every volume scan. What is the speed of the system, and then so the rest of this presentation really is about Well, what is this factor, or what is this wind gust ratio that we're going to be talking about that you would multiply by times the speed of the system to get the maximum wind gust? It could range from 1 up to well over 2. And so that's what we're going to go into. But before we do that, I want to talk a little bit about some of the wind gust estimation tools that are out there. Obviously, you can use straight up Doppler velocity. Of course, that depends upon the viewing angle and how close the storm is to the radar. In this case, this is the storm that took out the KUDX radar last July, and it was very close to the radar, and hence you could get a good estimate of the velocity just by looking at the Doppler. But again, that doesn't always work, because as you get farther away from the radar, the beam's much higher from the ground, and the viewing angle can be incorrect as well. Another feature that was developed by Ron Przyboliński and Gary Schmacher back in at least the 1990s, maybe a little bit earlier than that, in the early 90s, was the mid-altitude radio convergence signature. That also depends to a certain extent on viewing angle, and so it can't be applied necessarily in all situations. And I don't believe that allowed to give you an estimate of the speed, or the maximum wind gust, I should say. And then there are other signatures, such as the bow echo, which in this case of the bow echo oftentimes is an indication that winds already have been occurring. That's what's causing the bowing signature. And that, again, doesn't necessarily give you an estimate of the maximum wind gust. So then that leads to another study that we've been using since maybe 2005, 2006 in Rapid City. It was a very limited study by William Mahoney, who calculated the ratio between the measured wind gust and the outflow boundary motion. So that's what we refer to as the wind gust ratio, abbreviated WGR, just the wind gust that you measure divided by the outflow boundary speed. The problem with that study, it was a good study, and he looked at several other things, but he just looked at 30 gust fronts across the Colorado High Plains for just 2 summers. And while that might work well for Paul Schlatter, it's not going to work well for the rest of our offices. So we thought, well, let's expand this, and that's what Angela helped us do. And again, this can be evaluated every radar scan. So again, the thinking here is, if you have some ratio, which again, that's what this presentation is about, what ratio are you going to use? And then you can measure the outflow boundary speed. You multiply the two, you can get an estimated wind gust. So that'll bring us to the next question that we have here. I should make sure the responses are off. So using this 1.5 ratio as an example, what thunderstorm outflow speed would you need, or corresponds to the minimum severe wind gust threshold for National Weather Service warnings? In other words, what would you multiply this 1.5 times to get a minimum gust for severe thunderstorm warning? And this question is simply for me to make sure that I've been explaining things correctly up to this point. All right, so I'll show what responses we have, and there we are. Most people are showing 39, which is correct, because if you think, say it was 40, 1.5 times that would give you 60, and just under that is 58 miles an hour, which is our criterion. So very good. We'll move on to the next slide here. And one final thing to note about this wind gust ratio before I go into the data set and our methods is it's the ratio of the wind gust to the outflow boundary speed. But the wind gust itself is a factor of several things, such as momentum transfer, cold pool circulations, line end vortices. So there's multiple aspects that go into creating that wind gust. So our wind gust ratio is a fairly simple relationship. So keep that in mind, but we're not going to go into all those details. This relationship in and of itself works fairly well. Likewise, the outflow boundary speed is affected by the mean wind, density differences across that boundary, which itself are related to the phase changes, thermodynamics, and so forth. And the low level to mid-level shear is also important vis-a-vis the 3 ingredients method. You think of the low level shear and how that affects the propagation and forcing along the gust front. So these other things are important. We're not saying they're not, but if you look at the simple relationship here, it can work fairly well. So now we will move into our methods. And how did we calculate the wind gust ratio? Well, in order to make our study reproducible, and 3 of us were going through the calculations, we actually took 3 different periods. So let's say we have a 70-mile-an-hour wind gust measured at this time with this linear system. So then we calculated the speed of that system for the previous hour over 3 30-minute periods. So from 0 to 30 minutes prior to that report, 15 to 45 minutes prior, and 30 to 60 minutes prior. So we had 3 different storm motions. And of course, we then divided the measured wind gust by the motion for these 3 periods. So we had 3 different measurements, and then we averaged that together. And again, this was to make the study more reproducible, because we had 3 different people doing these measurements, and people can have slight variations. So that's how we came up with a final wind gust ratio for this particular system. And also, I should point out that we would identify the outflow boundary, or the leading edge of the precipitation. A spectrum width was a great tool for that, velocity as well, and reflectivity. Correlation coefficient, not so much, but these other tools are very useful. So that's how we calculated the ratio. In terms of the data, we gathered 943 reports of measured wind gusts from either ASOS or AWOS sites. We used measured reports because, as Roger Edwards and others noted in their study in 2018, estimated wind gusts can be inflated by as much as 20 to 25% on average. So we wanted to use something that, again, was consistent and reproducible. And we focused on areas that had a high air traffic because of the dangers associated with the winds, especially with aviation. And so each of these dots represents either an ASOS or an AWOS site. So if we just look at the area around KUDX, you see there are 3 dots. That doesn't mean there were just 3 samples there. It means that there are a lot of samples gathered at those 3 locations. We have the data broken up into regions, color-coded, and also delineated with lines. And so we try to cover the regions fairly equitably. But of course, in the Western US, there just aren't as many cases that fit these criteria. So for example, the West Coast, we literally only had 13 cases for that area, but we were able to get 90 in the West, and then several across the rest of the Central and Eastern United States. So we also broke up the data by convective mode into just 3 modes: supercell, linear, QLCS. So I should note here, it's QLCS or linear, so it might not fit your prototypical QLCS, but it is a linear feature, or disorganized. And there are a lot of different ways you can slice and dice convective mode. We wanted to keep it simple. And what I have shown here are perhaps the more complicated convective mode situation, just to show you the diversity. But on the upper row, we have supercells. Here was a line of supercells, and this particular one produced a gust. On the right, we have an HP supercell that prior to this time was very identifiable and discrete, but right at this point, it was merging into a line. So from here forward, it was a QLCS. From here backward, it was an HP supercell. And the gust was produced along the forward flank, or I should say the rear flank downdraft region of that storm. The middle 2 are linear / QLCS, so they would fall more into what we'd say linear feature. They have a common gust front with the gust occurring along the leading edge of that line. Here's another linear feature, but it's much shorter. It's not what you think of your several 100-mile long QLCS. And then finally at the bottom, we have disorganized. This one here, I believe, was in New Mexico, a very clear case where storms just developed rapidly. The outflow boundary shot out. Here we have a disorganized storm in an area where you had more of a linear feature. So again, even though you had this linear feature here, we classified the report because it came from this disorganized area of storms. So when we look at all of our data and stratify it by certain things, such as the convective mode, first of all, you'll note that for all cases, we had a little over 400 reports between 50 and 55 knots. But we have several reports that are less than 50 because we do want to look at null events. In terms of convective mode, if we look at that 50 to 55 bin, there's about 40 compared to a little over 200 for the linear QLCS mode, and then just under 150 for the disorganized or other. Most of the cases occurred in summer. Here there's a little over 200 with 50 to 55 knots, spring 100, and then fall and winter much less. And again, we wanted this to apply to all kinds of winds, so we definitely wanted to look at sub-severe winds. And then finally, we, through the help of Andy Dean at SPC, gathered all kinds of SPC mesoanalysis data, and we looked at two different types of searches. One was the nearest grid point, so let's just say there's a wind gust here in north central Kansas. We looked at the nearest grid point, and then the point with the highest surface theta E in that region. And typically it was the most unstable parcel. So over 68 variables that we looked at, and we applied a few statistical tests to see what variables showed the most promise. So that's a background of the data and the methods. Keith will be looking at the results, but we have one last poll question here, and that is, what does a small wind gust ratio near 1 mean? So does it mean that the wind gust magnitude is much greater than the storm speed? Does it mean the wind gust magnitude is similar to the storm speed? Or does it mean the storm is unlikely to be severe? So I'll give you a little bit of time here to fill out this poll, and then Keith will take over with the results. So here are the responses, and that's what I was looking for. So I think I did my job. Everybody understands the wind gust ratio, and so go ahead, Keith, and take it away.
All right, just to double check, see my screen okay?
Yes.
All right, thank you, Matt, for that introduction. All right, well, let's look at some results here. So in our data set, the average wind gust ratio was 1.68, so a little bit higher than that of the Mahoney study, which was 1.5, but the median was a touch lower. We had 1.44 compared to the 1.55 there. One key operational note about the general results before I move on here is that a relatively small percentage of cases had a wind gust ratio less than 1. So forecasters should generally feel comfortable using the outflow boundary speed as a lower bound for maximum wind gust in the majority of cases. And I will note as well that the standard deviation and interquartile ranges within our study were relatively large compared to Mahoney, which makes sense since we were looking at more diverse environments, regions, and so forth. All right. So based on the median 25th percentiles and 75th percentiles, winter cases tended to have the lowest wind gust ratios, whereas summer cases had relatively high wind gust ratios. And if you look at spring and autumn, they fell generally between the two, and they were rather similar with one another. Diurnally, the lowest ratios tended to occur in the overnight through the morning hours, and interquartile ranges were also relatively small in those time periods. When you look towards the afternoon and evening cases, especially kind of mid to late afternoon here, you see both higher ratios and broader interquartile ranges, particularly in, again, in that mid to late afternoon, to even through the early evening time frame there. So through the annual and diurnal distributions, one factor immediately stood out to us, and that was that the higher ratios tended to be associated with times where buoyancy tends to be higher climatologically. So one early hypothesis we had was that CAPE or some other set of thermodynamic variables may be correlated to the wind gust ratio. And we're going to be exploring those environmental controls a little bit later here in the talk. Likewise, there are relatively low ratios during the cool season and overnight to early morning hours when CAPE or buoyancy is generally lower. So another key point during these time periods with the overnight morning hours in the cool season is that the interquartile ranges are smaller, implying that you may be able to get a little bit higher confidence in the potential maximum wind gusts. When you look regionally, the Northeast, Midwest, Southeast, and also the West Coast tend to be associated with the lowest median wind gust ratios, whereas the plains have relatively higher ratios. But all of the regions have fairly narrow interquartile ranges when you compare those to, say, the Intermountain West, and the southern coast. And this subregion here is South Florida. If you remember the map, South Florida kind of had a few cases down near Miami and the southeast coast there. So we wanted to split those out just to see if there was much of a significant difference, and there really wasn't a whole lot of difference there. But generally that makes sense because you'd have a lot more disorganized cases in the Intermountain West and also kind of the sea breeze convection in those areas. So these results again suggest sensitivity to storm environments, but they also suggest potential sensitivity again to the convective mode, because your regions with the highest ratios and largest interquartile ranges are associated with that higher percentage of disorganized modes or supercell modes in the case of the plains, while those with the lower ratios have a larger proportion of our linear or QLCS cases. And if you do look specifically at mode, we see that there is indeed a pretty close relationship between the convective mode and the wind-gust ratio distributions. So the 75th percentile of the wind-gust ratios in linear QLCS cases is below the median for supercells and also for disorganized cases. And again, speaking about the interquartile range, the linear QLCS cases do have the smallest difference between the 75th and 25th percentile there. So continuing our subset results summary, there are these clear regional differences that are most likely tied to convective mode and also storm environment. And in terms of convective mode, a key result is that the linear QLCS cases had both the smallest wind-gust ratios, so those closer to 1 compared to the other modes, and smaller interquartile ranges. So again, that implies that we could have higher confidence in maximum wind gusts in these events compared to in the supercell and disorganized modes. Now, before looking into the environmental results, there are a few other odds and ends in which we were interested that we wanted to talk about here. A couple of these are related to the ratio itself. So first, looking at distributions separated by wind gust severity, it's clear that the significant severe wind gusts on the whole are associated with higher ratios than either the standard severe or the sub-severe wind gusts. And this isn't entirely surprising because, as you remember, the wind gust itself is the numerator of the wind gust ratio, so you would expect that sort of direct relationship. But interestingly, the median ratio for the severe wind gusts is awfully close to the Mahoney 88 average and median, right there, about 1.5, 1.55 in that area. On the other hand, the ratio distributions decrease as the outflow speed increases. And again, this is consistent with the formulation of the wind gust ratio since the outflow boundary speed is the denominator. But the decreasing interquartile range here also offers potential operational guidance because your confidence in forecasting maximum wind gusts can increase as you get to these progressively higher outflow boundary speeds. And then following the publication of the manuscript, we wanted to go back and determine if there was any sensitivity of these ratios to their distance from the radar. Because closer to the radar, it's a little bit easier to track the outflow boundary itself, whereas farther from the radar, we may be just looking at the leading edge of reflectivity as an example. So to assess this, we split the data set into near, mid, and far distances from the radar, which corresponded to less than 30 kilometers, 30 to 60 kilometers, and greater than 60 kilometers from the radar, respectively. And as you can see here, there is very little difference in distributions when considering the distance from radar. So that's encouraging given the potential slightly different method that was used depending on the distance from the radar. Now, of these three subsets, the key takeaway I want to focus on here is in the middle. And again, that's that the confidence in the observed maximum wind gusts may increase with outflow boundary speeds. And that's due to the diminishing interquartile range as you get to these faster and faster outflow boundary speeds. Now diving into the environmental results. For each environmental parameter, we determine its ability to discriminate between the high wind gust ratios, so those in the top third of the distribution, and the low wind gust ratios, or those in the bottom third. These tests were conducted for the entire population and all of the subsets, and we did it over the 68 parameters that Matt mentioned before. And in doing so, there were several parameters that showed statistically significant differences in means between these distributions. At the top of the list were mean wind magnitudes and low-level shear vector magnitudes, which showed fairly high correlation with one another overall. And generally, events with lower ratios were associated with higher mean winds. So in this case, we're looking at mean winds over the cloud-bearing layer, but the 850 to 300 millibar mean wind, which is available on the SPC mesoanalysis, was generally fairly comparable to this. This relationship is likely tied, at least in some degree, to the impact of storm motion on the wind-gust ratio. It may also be a function of storm organization, though that may perhaps be a more straightforward relationship with the vertical wind shear, which also showed pretty similar distributions to what's shown here. Cases with the lower mean winds would potentially tend to be less organized and may struggle to establish a distinct cold pool, meaning that the maximum wind gusts associated with that convection would more likely be tied to, say, a localized downdraft or downburst or microburst within the convection. But as the mode becomes increasingly linear, maximum wind gusts are more likely to be a function of the background wind profile due to vertical advection and momentum transfer. Now, while the kinematic parameters showed the most statistical significance in the data set, some thermodynamic parameters also showed considerable skill. In particular, we found that the low-level lapse rates and the surface relative humidity were both near the top of these statistically significant parameters. And like mean winds and the low-level shear, these parameters also showed a high correlation with one another, though it was an inverse correlation, of course, where steeper lapse rates tend to be associated with the lower surface RH. These two parameters are most likely tied to the potential for both vertical advection or momentum transfer of winds and also evaporative cooling, as ratios tended to increase with steeper lapse rates and lower surface RH. And this is pretty clear in the distributions for the low-level lapse rates shown here, although there is, as you can see, quite a bit of overlap as well, more overlap than what we saw with the mean winds. Mixed layer CAPE, it only showed a weak relationship with wind gust ratios, and this suggests that the integrated buoyancy may play a secondary role when compared to either the mean winds in the environment or the low-level thermodynamic characteristics versus looking at the integrated CAPE of the entire layer. Now, much of the time, and we're looking at the bottom here, it may suffice to consider just two factors when trying to determine a likely range of maximum wind gusts: convective mode and outflow boundary speed. So for instance, of the 186 linear and QLCS cases in the top quartile of outflow boundary speeds, 113 of these were in the lowest third of wind gust ratios. So that suggests that the wind gusts will be relatively close to the outflow boundary speed in those situations. But some environmental parameters may provide added context in certain situations. So, for example, of the 73 linear or QLCS cases with low outflow boundary speeds, so it was relatively rare, several parameters showed significant differences in means between these high and low ratio cases, including the surface relative humidity that was discussed previously, but also the most unstable parcel lifted level, the upper level storm relative wind magnitude, and some other factors as well. So just that added context can sometimes provide a little bit of guidance when you're getting set to start issuing warnings or not issue warnings in these types of situations. So let's walk through a brief summary of the environmental results in terms of what favors low and high wind gust ratios. And I'm going to get back to some of the climatological stuff here too. But linear and QLCS modes tended to favor a relatively low ratio in our data set, while the supercell and disorganized modes tended to be associated with relatively higher wind gust ratios. Environmental mean winds showed an inverse relationship with the wind gust ratios, so you had higher mean winds associated with the lower ratios. Likewise, if you had relatively high outflow boundary speeds, those also tended to be associated with lower wind gust ratios. If you had an environment seemingly favorable for evaporative cooling below the cloud base and the vertical advection of winds, so those with steep low lapse rates or dry low levels, those tended to be associated with higher wind gust ratios. And overall, this adds a bit more context to the previous results from early in the talk, touching on the wind gust ratios sensitivity to the diurnal and annual cycles. But again, those sensitivities to the different diurnal and annual cycles, they might very well be entirely explained by these sensitivities to the convective mode environment that we explored later in the talk here. But I wanted to point out again that there are a few factors that are associated with relatively low interquartile ranges. So that is occurrence in the cool season or nighttime to early morning hours, those occurring within the linear QLCS modes, and those associated with the fast outflow boundary motions. And again, the importance of the small interquartile ranges here is that they apply relatively high confidence in the maximum wind gust that may be observed in a given situation, because the 25th, 75th percentile of our observed wind gust ratios were fairly comparable to one another. So when you got to the very high end of our outflow boundary speeds, you're looking at something like a wind gust ratio of 1.1 to 1.3. So you'd be fairly confident if you know the outflow boundary speed, what the corresponding maximum wind gust will be. Now we wanted to close, which was a brief demonstration of calculating and applying the wind gust ratio. And for this, we're going to use the Table Rock Lake duck boat tragedy from a few years back now. The radar imagery here is from right around the time that the outflow boundary, which is clearly evident as the fine line here in reflectivity ahead of the convection, reached Table Rock Lake, which if you can see my cursor is right in this vicinity. If we step back half an hour, so you can see the convective line kind of retreating to the northwest with time as I step back, we can determine the motion of that outflow boundary, which in this case was toward the south-southeast at around 40 to 45 knots. Now, if we step back forward, let's consider what wind gust ratio would be needed for severe winds in this particular case. Let's first look back at the ratio distributions by region for just the linear QLCS mode. And we see that the middle 50% of wind gust ratios for the Midwest linear QLCS cases lie between 1.1 and about 1.4. And if you remember the map, southern Missouri was pretty close to the southeast as well, southeast region. It's fairly comparable there, maybe a little bit lower in terms of that 25th to 75th percentile. But given a motion of 41 knots, which was the specific value that I happen to calculate here, that range of wind gust ratios would provide us with a possible range of 52 to 66 miles per hour for a maximum wind gust. But we could potentially use environmental data from the event to try to provide a little bit more context for the values and to get a little bit more confidence going forward into warning operations. So let's start with the mean wind, which was shown to be the most skillful individual parameter discriminating between the high and low ratio cases. In this particular event, the mean wind was fairly low actually for Midwestern QLCS linear cases, around 25 to 30 knots. So if we use 25 knots, we see that this falls right around the median of the high ratio cases. If you use 30 knots instead, you're getting a little bit farther into kind of the mid ratio or maybe even lower end of the lower ratio distribution. In terms of a thermodynamic parameter, although we kind of talked about caveats CAPE and that other parameters may be a little bit more useful in this situation, let's just use ML CAPE for a nice integrated field as an example. What we see here is that the mixed layer CAPE in this event actually was quite high, somewhere between about 3,000 to 3,500 joules per kilogram for the SBC mesoanalysis. And in our data set, at least, that's more consistent with a high or mid wind gust ratio than our lower ratio cases. So with that environmental context, we may want to hedge toward a higher wind gust ratio. And if you look at the distributions for just the Midwestern linear QLCS cases, we see that high ratio cases can have awfully large ratios actually. About half the distribution here is over a wind gust ratio of 2. But this was a complex case. The environment, the convective line itself, are both rapidly evolving. However, I'd say that there's probably some evidence for at least going with ratios somewhere near the middle of the distribution for the region in the convective mode. And that would put you solidly within that severe wind gust range in this situation. And Springfield anticipated and messaged this threat very well for this particular case. And this was just one example, but again, it provides an idea of how you can use convective mode, region, environmental data when you're trying to nail down a probable range of wind gust ratios in order to aid you when you're assessing a potential maximum wind gust. Now, I wanted to kind of bring up something that's hot off the presses here. Matt has created a script now that can provide a distribution of wind gust ratios within a set radius of a given lat long point. In the last couple of weeks, he's recently implemented some additional ways to partition the data. So looking at convective mode or time of year or associated environmental data. I will say that comes with the caveat that you'd get increasingly smaller sample sizes with additional criteria, but it still may be interesting to look at that kind of stuff for you in a real-time setting. So for this particular Table Rock Lake case, if you don't enforce any environmental constraints and you take the summertime QLCS cases within 500 miles of the point, you find that the inner 50% of the wind gust ratios would correspond to a maximum gust of 56 to 76 miles per hour. You can also calculate with the script the probability of severe winds. So in this case, given the subset of our population that was represented, it's 66%. Now, interestingly, for this case, when you do enforce the environmental constraints, the probability of severe wind decreases slightly, but notice that your sample size is also very low. You just had 11 cases included in the distribution here. So this suggests that the given environment for the Table Rock Lake case was a bit of an outlier compared to the rest of our data set. And given that smaller sample size, there may not be quite as much confidence in that range of potential wind gusts. So going forward, one of our goals as well in terms of future work is to expand upon our data set so we could potentially get some more representative distributions as you're using this tool in operations. So I'll jump back to the overall summary slide and just note that for more information, you can see the article that was published last year in Weather and Forecasting. I do want to say thanks again to Angela Mose, who began this research with our office as a Holland student. As Matt mentioned, she's now our Pathways intern, but she is finishing up her master's degree at University of Oklahoma and will be joining Cheyenne later this year. So thank you for your attention, and we're happy to address any questions that you have at this time.